Swayam Prabha. Digital India. Educated India.
So let us look at this concept with an example. So the example that I have is as follows. This is a very classic rigid body problem, which says that suppose we have a disk, right? And the disk is rolling on the ground, right? So I'm sure most of us drive on the road, and typically when a car drives on the road, the wheels, they rotate on the ground, right, without having friction. So if we have friction between the wheels and the road, then the car is going to slip, especially when we have an icy road, and that is a very dangerous situation. So I'm not talking about the dangerous situation. I'm thinking about a situation where the car is rolling on the road and the wheels are moving. So let's say the wheel is moving with some speed u, right? The car is moving with some speed u, and I want to find the velocity of any point P on the wheel, right? So which means that if the wheel is rolling, which means that it must be rotating with some angular velocity omega, right? And omega needs to be clockwise. Why? Because if it is not clockwise, the wheel is not going to move towards the right. If the wheel is moving towards the left, then our omega will be anti-clockwise, right? So that is a common intuition here, right? So that is not the case we are talking. So now, so let me write down this problem, and I think it will be clear what I am trying to find. So the problem says a circular wheel of radius b rolls in a straight line with speed u on a fixed horizontal table. So we need to find the velocity of its particles, right? We need to find the velocity of its particles. So notice, as I just said, we see that particles, let's say in this case the particle P, right? So the P, let's say the particle P is at a distance rho. I need to find all these quantities, and the particle P is of course rotating with an angular velocity omega. So now the Vp, the velocity of the particle at any given point P, is u times u I hat. So u is along the x direction or the forward direction, and then due to rotation we see that, well, we need to show you the geometry here. So from here we see that u is this, and suppose the point P is this, and suppose our angle is theta here. So theta is going to be here, and what else do we have? So what we have is that rho omega is the rotational component of the velocity. This is acting tangent to the point P, and so this is our 90 minus theta. And now from here I can find my angular component of the velocity. So this is going to be rho omega times cos theta I hat minus sin theta j hat, right? And we see that this is equal to u plus rho omega cos theta I hat minus rho omega sin theta j hat, right? Okay. So then we also have to include the fact that the wheel is rolling, right? So it means that there is no friction between the wheel and the fixed road. The disc is rolling, the wheel is rolling. So which means that if we were to find the velocity at, let's say, the point Q, so V at Q, so what is V at Q? So V at Q is U plus rho omega. Notice that our angle theta is this particular angle. Well, I need to make sure. So what is this angle? Hold on. So theta, with this specification, theta is going to be this angle theta. Okay, so this is my angle theta. So this is going to be 90 minus theta. So this is going to be 90 minus theta, and this is going to be theta. Okay, so this is theta. Okay, so this is this is theta. Okay, so theta is the angle with respect to the vertical. Okay, so now when theta is 180 degrees, which is, we are looking at a point which is on the road. So we have cos of pi times I hat minus rho omega sine of pi j hat, right? So this is going to be u minus rho omega I hat. Now we expect, since the wheel is rolling, the velocity of the wheel at point Q, which is touching the road, will be 0 because the road is fixed. So the wheel also will have the particle at the edge of the wheel, which is on the road, must also be fixed. Otherwise the wheel is slipping, right? So we have that this has to be 0, which means that our omega comes out to be u over rho. So from here we find the angular velocity in terms of the radial velocity, and from here we can find our general velocity Vp to be u1 plus rho by b, rho by, well, what do we have? Well, hold on. I think at Q, our rho is also the radius of the particle, right? So it is the radius of the particle, because radius of the wheel. So the radius of the wheel is b, right? So I have that omega is u over b, right? So now we have the velocity, the general form of the velocity is the quantity this, which is this I hat minus u rho by b sine theta j hat, right? Okay, so then we see that on the circumference, what have we got? So the speed of the particle p on the circumference, on the perimeter is going to be when rho, the distance from the center, is b, right? So in that case my v is going to be u1 plus cos theta I hat minus u sine theta j hat, right? So when rho is equal to b, and that is what my velocity is on the perimeter. So that is the problem. So that is this problem neatly highlights how to find the total velocity of a particle, the particle on a moving as well as the rotating object, right? Okay, so then I need to also briefly talk about the concept of so-called reference frame. So what is this idea of reference frame? Reference frame. Okay, so especially, we may have some reference frame which are fixed. Well, nothing is fixed. Even Earth is not fixed. Earth is also rotating. But it is always convenient to do a problem when we have a starting reference frame which is fixed, right? And then we can have another reference frame which is moving with respect to the fixed frame. So we will associate certain terms with these fixed reference frame and moving reference frame. So let's say that the motion of the particle P be observed the motion of the particle P be observed from frames F, which is denoted with the origin O, I, J and K, right? And F prime which is O prime, I, J, K. Why have I taken the same coordinate axis? Because I am assuming that F prime does not rotate with respect to the original frame F. If it doesn't rotate, you expect the coordinate axis to remain the same, that is fixed, the direction to be fixed, right? And hence coordinate axes are matching, right? Okay. So let my position vectors in respective frames be R and R primes, be the position vectors in F and F prime, right? And we see that the velocity can be defined similarly using the position vectors. So we see that the velocity V, hold on, before I move ahead with the velocity, I do have a relation between the position vectors. This R and R prime are related. That is, R and R prime are related as follows. Where suppose we have this fixed frame, let us say this is my frame F and my frame F prime which is moving, right? And I need to find my position of a point P which is R prime in the moving frame and it is R in the fixed frame. But then the other variable is the distance or the displacement of the origin of the moving frame with respect to the fixed frame. So D is the displacement of the origin O prime with respect to the origin O of the fixed frame, right? So that is D. So from here when I differentiate, I see that dr dt is equal to dr prime dt plus d dt, right? Now the crucial part here is we have to talk about with which frame are we differentiating, with which frame are we evaluating all these quantities. So the idea is we are evaluating these quantities with respect to fixed frame. So dr dt in frame F, this is in frame F, this is in frame F, right? Now if then comes the crucial fact that these two frames are not rotating with respect to each other, right? So if F and F prime and F do not rotate with respect to each other, right? Do not rotate with respect to each other, then I can have that this quantity, this speed in the frame dr dt in F is dr prime dt in F prime, right? Since the frames are not rotating, then the velocity, that is the change rate of change of the position vector with respect to the fixed frame, is the same rate of change of position vector with respect to the moving frame, right? And then I can say that this is also equal to v prime, that is the velocity of the particle in the moving frame, right? So now we have a new result which says that the velocity of the particle in the fixed frame, notice the prime denotes the moving frame. So v, which is the velocity in the fixed frame, is v prime plus d dt, which is capital V, that is this is the velocity of the fixed frame with respect to the velocity of the fixed frame with respect to the velocity of the moving frame with respect to the fixed frame, right? The velocity of the moving frame with respect to the fixed frame. Okay, so that is the result that we have. That is the velocity of the particle in the fixed frame will account for the velocity of the frame as well. That is the velocity here, right? Okay, so let us look at a quick example related to this moving and fixed reference frame. A very interesting example. So, suppose we are driving a car, right, on a road, and let us say that the road is 1 mile. Let us say that the road is 1 mile in width, right? So we are driving a car, let's say on the edge of one road, and let us say the car is being driven at some velocity, let's say u, right, u, and suddenly we have, let's say, a tornado, right? So we have a tornado which is let's say perpendicular to the motion of the car. So let's say v, with velocity v, and now I need to figure out if originally without the tornado, the car was moving in a straight line, then what is the impact of tornado? How is the car going to shift to a new velocity and a new direction, right? So let me write down the problem, right? So the problem is a road is 1 mile wide, with 1 mile wide, and well, this is a road which is the wind. Well, let's not talk about tornado, which is a bit of extreme. Let us say that this is wind, right? So a road is 1 mile wide, with wind flowing uniformly, right? Okay, so then it turns out that the problem is that we have a car which a car at full speed takes about 12 minutes to cover the width of the road, right? So this particular statement tells about the actual velocity of the car. The car is taking 12 minutes to cover 1 mile, right? That is, so let us now try to draw a more accurate figure here. So we have a wind which the car can take, has a velocity v, and it can take 12 miles to cover the width of the road, which is 12 minutes to cover the width of the road, which is 1 mile, or 12 minutes times 5 is 60 minutes. So the car is driving at the rate of 5 miles per hour, right? So 12 5 is 60, so 5 miles per hour. So it takes the car 12 minutes to cover the width, when along with the wind, right? So the wind is blowing like this. So let us say this is the wind W. So this is my wind, and the car needs to cross the road. It needs to go across the other side of the road. And when you have a wind, then the car is taking about 12 minutes to cover 1 mile, which is 5 miles per hour. So the wind is perhaps slowing the car down or speeding the car up, right? And then it takes the car only 3 minutes when the wind blows downstream, right? And 12 minutes to cover the width with upstream wind, okay, with upstream wind. So we see that upstream wind, what else? So then this question says is what is the shortest time time it takes the car to cross the road at the nearest point. Okay. So again, let us redraw the diagram. So here we have a road which is 1 mile long, right? And the car needs to go across the road, right? So the problem is that a wind is blowing, and either the wind is blowing downstream or the wind is blowing upstream, right? So when the wind is blowing upstream, it is actually pushing the car. Well, so let us say our velocity of the car is Vc, right? And the velocity of the wind is Vw, right? So what happens is when you have a downstream situation, then the wind is helping the car to speed up, right? So we have that so we have a downstream. We expect that Vc and Vw are along the same direction, right? So Vc and Vw are along the same direction, and if we have an upstream, then we expect that Vc and Vw are in the opposite direction, right? So what we see is that in the downstream situation, we expect that the total velocity is Vc plus Vw, right? And in the upstream situation, we have that the total velocity is Vc minus Vw. So the wind is actually resisting the car. So now some information is given. Well, I think I have written the problem in the opposite way. So the first information was that it was taking 12 minutes when the car was moving. Well, it was moving upstream, right? This is right. Okay, so this is right. Okay, so now in the upstream situation, when you have a velocity v, which is Vc minus Vw, right? It was taking 12 minutes to cover 1 mile, or it was taking 5 miles. The net speed of the car was 5 miles per hour, right? So this was in the upstream situation, and in the downstream situation, the net velocity was Vc minus Vw, which was taking only 3 minutes to cover 1 mile, or it was taking going at a speed of 20 miles per hour, right? So from here I can find what is Vc. So Vc comes out to be 12.5 miles per hour, and Vw, the speed of the wind, comes out to be 7.5 miles per hour, right? So the car is trying to cross the road. So Vc, and the wind is either blowing this way or the wind is blowing this way, either downstream or upstream, and either way the car is going to shift its direction because of the wind, right? Now this question is, what is the shortest time it takes for the car to cross the road, right? Now if the car, typically the shortest position for the car will be the position which is perpendicular to the starting point for the car, right? But if the car wanted to start wanted to reach a position which is perpendicular, it must go at a distance which is at a direction which is at an angle, right? See, if we have this angle, could be this direction or this direction, depending whether the wind is blowing upstream or downstream, right? But the car has to go at an angle because the wind is going to push the car in the direction normal to the road, right? Because eventually we want to go normal to the road, right? So what is this angle? This angle, we see that this angle cos alpha is going to be what? So Vc cos alpha is going to be V upstream, right? So we have what is it? Upstream. So we have upstream is VC. So we have VC is VW. So VW. This is VW. So VC cos alpha is VW, right? So from here I can find that my VC is 12.5, cos alpha is VW, which is 7.5, or cos alpha comes out to be 3/5, right? And from here now I need to so cos alpha comes out to be 3/5. Is this everything fine? Well, this alpha is right. Okay. Well, this, I think the diagram, well, we need to draw the diagram properly. I think something is not adding up. So we have VC and we have VW, right? And this is alpha, and this direction, sorry, this is not VW here. VW. So we have VC. So VW by VC. VW by VC is tan alpha, right? Or so VW by VC is tan alpha. So from here I can find, from this direction I can find. So VW is VC cos alpha. Hold on, sin alpha. Sorry, sir, sin alpha. Okay. So this is sin alpha. Okay. So so from here I see that my sin alpha comes out to be 3/5, and that defines my angle of tilt, right? So now I need to go along this direction, and this direction will be nothing but the net velocity of times cos alpha, because the sin alpha is along this direction. We need to go along the perpendicular direction, right? So we have that the velocity along this particular direction comes out to be v cos alpha, which is coming out to be 4/5, which is around 10 miles per hour, and which means that from here we can find that 10 miles per hour is nothing but 6 minutes to cover 1 mile, right? So the shortest time it takes for the particle to cover 1 mile is 6 minutes for the car. Okay, so let us wrap up our discussion here, and in the next module we will start with the discussion of the standard Newtonian mechanics. So thank you very much for listening.